Hello and welcome back. In this video we want to take a look at how we can use convolution neural networks in Tensorflow and Keras. Convolution neural networks play a large role in many machine learning applications because they allow us to analyze images and then use this, for example, for image classification. Before we dive into the material science aspect, we want to do this on a practice dataset called MNIST. And these data contain a large number of handwritten digits in the range from 0 to 9. And our task here is then to classify which digit is shown in the next image. These images are snippets of 28 by 28 pixels, so we have 784 pixels that we need to analyze and 10 digits, so 10 classes. We load the data, and because this is such a popular data set, there are a lot of convenience functions that do that for us. So we have this data here, and then we can look at an example. We just randomly grab the index 1, 2, 3, 4 and see what it's like. So we have the image data, and this is labeled as a 3. You can see that if you squint a bit, that this is indeed a handwritten number 3. Earlier we said it's a grayscale, black and white image. We can see it here now in grayscale. This is because of the anti-aliasing. So all of these things make it, if you make this image small, look a bit nicer instead of just having a box where the black dots go. So first of all, we need to define the shape of the tensor. And the tensor is like the object that holds the image, the input. So we have the length of the training and the test data. So these are the number of samples that we want to analyze and split into test and training samples. 28 by 28. This is what we have given in the data set, and we only have one color, the grayscale value. We also need to normalize the color range by dividing this, otherwise it will not work because the system assumes that the colors are in a given range and we have to stick to this. So we have our training data, and here the reshape part gives us the shape of the input tensor, notably the 28 by 28. This is the image dimension, and 1 has only one color channel, and we use this as float numbers. And this is the normalization we just mentioned. So now we have a very simple model. You can see what you, if you do this yourself, should end up with. We have one convolutional layer, a pooling layer, and put this together into a dense layer, drop out for realization, and then another dense layer for the final classification. And this is the 10 classes, 0 to 9, that we want to discriminate. And then we can build our network with this. You should be able to do this code yourself. We can compile the model and then fit it with this Keras API. So we have the history object that contains the test and training, error as we go along. Fit the model for 15 epochs, and then we can evaluate this on the test sample. So if we plot the history object, we can see that the loss function goes down, the accuracy goes up as we progress, and since this is a fairly simple problem for a convolution neural network to learn, it doesn't take long to achieve quite high accuracy. This is okay on the independent test sample for us. More complex models can achieve even higher accuracies, and you can find a list here, but because this is such a simple data set, this suffices for us. We can also do a confusion matrix that should end up like this. Ideally, we want to have a diagonal line, so each digit is a prediction on one axis, the horizontal axis, and the true assignment of the y-axis, and ideally this should be just a diagonal. You can see that there are only a very few mistakes made by this network. So we can also come up with a more complex network. You can, for example, then use the following approach where you have more convolutional layers with pooling layers, and then you follow the same logic, and this, as you can see, for the simple model already starts to introduce some wiggles, and the performance improves not substantially that much for our application.